The debate over the Big Bang hypothesis has continued to heat up in the first 2 months of 2024. The biggest discovery that's fueling the debate, among several, is the discovery of what is called the Big Ring. And in this episode, we'll see whether the Big Ring is ringing out the Big Bang. So what is the Big Ring? Well, the Big Ring is a huge circle of galaxies in the sky. This circle of galaxies is so large in the sky that if it was visible, it would be 15 times the diameter of the full moon. It's not visible to the naked eye because these galaxies are much too faint. But a graduate student in astrophysics in the UK, Alexia Lopez, discovered them by looking at data sets that showed the absorption of light from background quasars being these huge explosions in space. And you could tell from the redshift of the absorption lines, the way that gas or plasma was absorbing the lines, that there were intervening galaxies in this ring. And she did, and her colleagues did a number of very intensive statistical tests, and they showed that this ring was a real object, and the chances of just being a random pseudo-ring that just looked like a ring by chance was less than 1 in a few million. Now, the important thing about this ring is that when you determine how big it is in real life, in linear dimensions, you get dimensions that are at least 1.2 billion light years across. Now, why is 1.2 billion light years across so important? Because objects could not form of that size in the time since the Big Bang. It would have taken much longer to form these objects. Now, before we get deeper into that, people who have been watching this series or have been paying attention to cosmology might recognize the name Alexia Lopez, because this same graduate student, who really has earned several PhDs by now, back in 2021, just 3 years ago, had discovered another extremely large object by the same method in almost the same part of the sky. She discovered the giant arc, which caused a bit of a stir back in 2021. And this was an even bigger object, but not a full circle, just an arc of a circle. So the reason why these discoveries are putting extreme pressure on the Big Bang hypothesis is because it would have taken too long to form these objects. There just wasn't enough time in only 14 billion years. And to understand why this is true, you don't need to think in 10 dimensions or be able to solve the equations of general relativity. Even though you won't be hearing this from too many other people, it's easy to see why this is actually true. We can tell how long an object takes to form from the velocity at which particles within this object are moving, divided into its physical dimensions. So we can tell from redshifts, from the spread of redshifts, that objects in our present-day universe, galaxies in our present-day universe, are not moving a lot faster than about 1/500th the speed of light. Now that's still pretty swift because we're talking about something of the order of 500 kilometers per second. But it means that it takes 500 years to cover 1 light year. So if we hypothesize with the Big Bang hypothesis that the universe has only existed for 14 billion years, well, 14 billion divided by 500 is about 30 million years. So, in essence, we're looking at objects that should not be more than 30 million light years across. Now, of course, in the Big Bang hypothesis, the universe is expanding. So, farther back in time, by this hypothesis, objects would have to travel lesser distances, but they'd have less time to do that. So the mathematics ends up pretty simple. Basically, high school algebra, that you can put another factor of 10, if you stretch it another factor of 20 into that equation. So you can form objects that are as big as 600 million light years across, but not 1 billion light years. By any mathematics, objects 1 billion light years across would take 30 or 60 billion years to form, far more time than the time hypothesized since the Big Bang. So, simple conclusion, the Big Bang hypothesis predicts that no objects in the universe should be larger than about 600 million light years. Well, the giant ring is the latest of a number of objects that have been discovered, such as the giant arc, that are much bigger than 600 million light years across. So this is a total contradiction of a basic prediction of the Big Bang hypothesis. And as we've been explaining in all of our videos, the key test of the validity of a scientific hypothesis is whether it makes correct predictions about observations that are to be made in the future. And this is a completely wrong prediction. But you actually won't be hearing that from other people except us right now, because there is the emperor's new clothes effect, that if you say, well, the Big Bang didn't happen, you must be stupid or unfit for your job. So there's a little hesitancy to say that. On the other hand, people are very concerned about the Big Ring. Now, why is this? Well, the Big Ring contradicts another basic feature of the Big Bang hypothesis, which is one of the assumptions on which the Big Bang hypothesis is based. And that's what's called the cosmological principle. And you will hear, and you might have already heard from many other sources, that the Big Ring seems to violate the cosmological principle. Now, what is the cosmological principle of that great title? The cosmological principle is a very simple assumption. It's the assumption that the universe at a large enough scale is completely homogeneous and isotropic. In other words, it has no structure at a large enough scale. It's smooth like a well-made pudding. This hypothesis is fundamental to the theoretical basis of the Big Bang hypothesis. You may have heard incorrectly from some people that general relativity predicts that the Big Bang must have happened, that the universe must be expanding or contracting. Well, that's not true. What is true is that the equations of general relativity predict an expanding or contracting universe if you also assume the cosmological principle that the universe at a large enough scale is completely homogeneous, the same density at every point, and isotropic, the same density in every direction. If there is structure at the scales that are larger than that predicted by the Big Bang, larger than the scales at which objects could form in the time since the Big Bang, larger than the scale of about 500 million light years, then the cosmological principle is wrong. If there's structure at these huge scales, then that completely undermines the basic hypothesis that underlies the Big Bang and the expansion of the universe. If the universe isn't homogeneous, then the equations of general relativity don't predict whether that the universe is either expanding or contracting. In fact, those equations in the general case can't even be solved to give one single prediction. So that contradiction of the cosmological principle is what people like Sabine Hassenfelder and others are saying is of great concern. It's of great concern because this is not the first object that contradicts the cosmological principle. Again, there was the giant arc discovered just 3 years ago. But Alexia Lopez and 20 of her colleagues wrote a paper last year that listed all of the more than a dozen observations over the past several years by many groups of researchers that have shown that quasars and galaxies and gamma-ray bursters, very bright explosions, all of these objects are clustered on scales that are much larger than those predicted by the Big Bang hypothesis. Billions of light years across. And they conclude that the cosmological principle is not supported by observations. And to get back to the importance of the cosmological principle, the cosmological principle was assumed by the founder of the Big Bang hypothesis, Abbé Georges Lemaitre, as a basic way of solving the equations of general relativity. Now, the equations of general relativity are quite complicated. Matter of fact, Einstein himself, in developing them, found that it was a big headache to deal with these four-dimensional equations. To solve these equations analytically, you had to make simplifying assumptions. Well, Lemaitre and Einstein himself made the assumption that the universe was homogeneous. Now, why did they make that assumption? Well, they made that assumption because it was the only way to get simple solutions, analytical solutions, solutions you could write down of general relativity. Now, that's not a good reason to make a scientific hypothesis. The equations that we can use to describe the universe are often easy to write down. If they're useful, they pretty much better be easy to write down. Maxwell's equations can fit on a t-shirt and fit on many millions of t-shirts. But Maxwell's equations that describe electromagnetism are not, in most cases, easy to solve. even with giant computers. Well, who said they should be? Nature doesn't have to make things easy for hard-working scientists. So simplifications, approximations, almost always have to be made to get these equations to give useful predictions. But the correct way to make the simplifying assumptions is to look at nature and try and say, well, what approximately fits what we observe in nature? What approximations can we use to say, well, you know, in the famous joke, the cow is almost like a sphere. If you make the assumptions instead to make your job easier, to make the equations easier to solve, you may be solving equations that have nothing to do with what nature is like. And the funny thing is, at no point in the last 200 years of observing the sky have objects in the universe looked homogeneous. At every point, as our telescopes have penetrated out further and further in space, we always see a clumpy universe. We see stars isolated from each other. We see clusters of stars. We see galaxies isolated from each other. We see galaxies clumped into big, giant clusters of galaxies, and those clusters are strung out like beads along the string of filaments which are distant from each other. And those filaments, those supercluster filaments, are lumped into even greater structures, such as the big ring and the big arc. There is structure at every scale, and we've seen those structures every decade we look out further and further. There was never a time in the whole history of astronomy in the last centuries that we saw a homogeneous, smooth universe. So this was an unjustified assumption, but it did make the equations easy to solve, and that led to the prediction that the universe must be expanding or contracting. Now, I and other people like to say that there's a sort of the lamppost effect. There's an ancient joke, which all of you probably have heard, about the inebriated person who is looking around under the light of the lamppost. And a sober person comes along and says, "Can I help you? What are you looking for?" And the drunk says, "Oh, I've dropped my keys. I can't find my keys." And the person asks, "Well, where did you drop them?" He says, "Oh, way over there on Epsom Street." Epsom Street? "Oh, why are you looking for them here under the lamp?" The drunk says, "Wow, the light's much better here." That's like solving an equation with an assumption that makes the equation easier to solve. The light's much better, but it's not where nature dropped your keys. So what these new discoveries are is sort of pointing out that the keys are not there. Now, in preparing for this episode, I actually looked up when this ancient joke was first reported. It seems that somebody made it up around 1924, just exactly 100 years ago. It was in 1927 that Georges Lemaitre wrote the paper that started what is now called the Big Bang hypothesis, just 3 years after the joke. So maybe that was part of Dr. Lemaitre's inspiration, was to look under the lamppost. Nature isn't cooperating with the Big Bang hypothesis that the universe is not smooth and homogeneous. And therefore, there's no reason to expect that there was or is an expansion or contraction of the universe, and that that is the explanation for the well-known Hubble relationship, which correlates a redshift with distance. And the existence of these objects is not something that is really a recent concern. Even back in 1988, 36 years ago, no less an authority than Joseph Silk, a leading proponent of the Big Bang, said that if objects this large were discovered, you would have to question the Big Bang hypothesis. So the Big Ring completely contradicts the predictions of the Big Bang expanding universe hypothesis. Well, what if the universe is not expanding? Then, can we compare the Big Ring with predictions that were made on the basis that there was no Big Bang? Well, again, as we've explained in earlier videos, if the universe is not expanding, then measurements made at high redshift imply linear dimensions that are larger than that are implied if you assume the universe was expanding. At the redshift that the Big Ring is, which is a redshift of 0.8, objects, if the universe is not expanding, if space is as space is in this room everywhere, then objects are about twice as big as if you assume the same objects in a universe that was expanding. So if we assume that the universe is not expanding, then we get these values. The radius of the Big Ring is about 1.1 billion light years, as opposed to its diameter being 1.2 billion light years. And the radius of the circle that the giant arc is part of is about 5 billion light years. Well, did anyone make predictions of such objects on the basis of a non-Big Bang universe? Well, as a matter of fact, I did. In papers that I published back in 1986, 38 years ago, I used the simple assumptions that electromagnetism, plasma physics, and gravity operated on all scales in a universe that did not originate in a Big Bang. On that basis, I showed that primordial filaments, giant vortexes of plasma, should form and start contracting when they were 4.9 billion light years in radius, really close to the 5 billion light years of the giant arc. They would compress down to 1.2 billion light years in radius, again, really close to the 1.1 billion light year in radius of the Big Ring. But these predictions go beyond the size, because these predictions were that these vortices were formed by the magnetic fields of giant currents, by the pinch effect, which we observe here in the laboratory, and at all scales throughout the universe, which draws currents together. And this draws currents into characteristic forms, which are called force-free vortices, which have tighter and tighter helixes around the outside and straighter filaments towards the inside, sort of like the Veil Nebula. And what do we observe, or what did Alexia Lopez and her colleagues observe? The Big Ring is actually a tightly wound helix. So not only is the dimensions of the ring and the arc accurately predicted by this 36-year-old paper, but so is the form of the ring, the fact that it's helical. And this comes not from any arbitrary assumptions, but simply from the idea that the electromagnetism and gravity that we observe on the Earth and in the solar system function in the same way, at least up to scales of billions of light years. And that the universe had trillions of years for these objects to develop, and therefore that, of course, there was no Big Bang 14 billion years ago. So the summary is, the big ring is important because the big ring contradicts both the predictions that come from the Big Bang and the basic assumptions that underlie the Big Bang theoretically. But the big ring's observations are totally supportive of predictions that were made on the assumption that there was no Big Bang. That's why a lot of people are really concerned about this big ring observation. And what you see in the commentary is that supporters of the Big Bang are sort of fragmenting, because there are some hardcore supporters like Ethan Siegel who are just poo-pooing these many observations and saying, oh, they did the statistics wrong. All of these people are just wrong. It couldn't be. And there are other people like Sabine Hassenfelder and quite a few others who are saying, well, this is a real problem. This could undermine the cosmological principle. And that fragmentation is going to shape the next phase of the Big Bang debate. But before that, I have a request, your support. LPPFusion's researchers are not backed by billionaires. Our work, both in fusion and in astrophysics, are supported by thousands of individual investors. Unfortunately, that's just not enough. To hire the people we need to achieve maximum speed in our research, we need another $1 million a year. You can provide that. Not by yourself, to be sure. But we have 12,000 subscribers to LPPFusion's YouTube channel. If just each of you donated $10 a month to LPPFusion, that's only 3 dimes a day, or you invested in LPPFusion $100 a year, we would get another $1.2 million per year. Our work can provide energy that is 90% cheaper than any available today. Safe, clean, unlimited, no greenhouse gases, no pollution, decentralized energy, a better future for all of us. So, thanks for your support.